So 12.3 is going to be the binomial distribution. I'm going to start this off with, it's kind of a motivation problem here. Going back to the bubblegum flavored toothpaste we had in 12.1. 9 out of 11 men enjoy it, 4 out of 7 women enjoy it. And the question I gave you was, what's the chance of randomly picking 3 men in a row that enjoyed the flavored toothpaste? Now, what we decided to do was multiplication rule. 9 out of 11, 9 out of 11, 9 out of 11. Remember, that's a parameter. That 9 out of 11 is not changing. That's describing the entire population. So just pulling one man out, it's not going to change that 9 out of 11. Population's too big for that. So we can just set up our 3 fractions here, multiply across and get our answer. Now if I change this question a little bit and say, what's the chance of picking 5 men and having exactly 2 of them enjoy the flavored toothpaste? Well, out of the 5 men, 2 of them enjoyed, so that's 9 out of 11 and 9 out of 11. Now we have those other 3 people. None of them can enjoy it, so that means the opposite, the complement, would be 2 out of 11. 2 out of 11, 2 out of 11, 2 out of 11. And that would give us our answer, right? Well, kind of. It's getting there. This says that the first person likes it, the second person likes it, and the next 3 people don't like it. But if I ask 5 people, is that the only way that can happen? Maybe the first person likes it, the next 3 don't like it, and the last person likes it. Maybe the first 3 people don't like it, and the last 2 people like it. These are all the things you need to think about. How many different ways could we set up this problem? Because in probability, we need to think of every single outcome. So it's not only 2 people like it and 3 people don't like it, but where are those people? We know exactly 5 people we're going to ask, but then where are those 2 people that like it going to land? This is what a binomial distribution does. The binomial is going to figure out if we have a set number of people or set number of events are going to happen, how many ways can those successes happen within that event. For this one, asking 3 people, all 3 people like it, that's the only way it can happen. 9 out of 11, 9 out of 11, 9 out of 11. 5 people and 2 people liking it, that can happen a whole bunch of different ways, and you have to take every one of those ways into account. And that's what the binomial distribution is going to do for us. So, 12.3, the binomial distribution. To use the binomial distribution, there's some rules that have to be followed. Okay? You must have a certain number of trials. In that one example, our certain number of trials were 5. We were asking 5 people, do you like that flavored toothpaste? So that would be our set number of trials. It can't be open-ended. We have to say, here's how many we're going to look at, what's going to happen within that set. You can only have 2 outcomes. So you either liked the toothpaste or you did not like the toothpaste. Okay? There was no middle ground. You weren't rating it 1 to 5. You either liked it or you did not like it. True, false, yes, no. All these things have to have 2 outcomes, or all the situations can only have 2 outcomes. And it must be independent events. So what it means by independent events is that 9 out of 11% of success did not change. 9 out of 11 stayed 9 out of 11. Think about how big your population is. Like that was the population of males. Pulling one male out is not changing that 9 out of 11. Okay? Rolling a die, the probability is not going to change every time you roll the die. It's always 6-sided, 1, 2, 3, 4, 5, 6 on the die. Okay? So these are the things you need to think about. These are the rules that you need to follow. And just for reminder here, I want you to round to the 1,000th decimal place. So again, your answers are going to show up as a decimal form. Just make sure you round it to 3 decimal places. And that's just my rule. That's how I want your final answers to look, in percent with 3 decimal places. Now, we're going to look at both the formula and the calculator function. So the first thing we're going to look at is the formula. Okay? For the formula, we have combination NCR, which we actually get a lot more into this when we get into 12.4, when we get into the counting. Okay? Just know that this part is going to take care of all of the ways our situation can happen. How I kept writing up 9 out of 11, 9 out of 11, and how many times we get 2 out of 3 or 2 out of 11. all those different combinations of way it can happen. That's what this part does. P to the r power and q to the n minus r power, that takes care of our probabilities. Our probabilities of a success and our probabilities of failure. How many ways can they look? Okay, so here we have n is our total number of trials, r is the number of successes, p is the probability of success, and q is the probability of failure. Since there's only two outcomes, these are complements of each other. They have to add up to 100%. So P plus Q adds up to 100%. Because usually the problem's only going to give you the probability of success. You then have to figure out what Q is going to be. Okay? So you have total number of trials. And the C, I know it's not on here. The C is going to be the function we use for the combination, for finding those combinations. Right? So there's the formula. I am going to put here, I always think it's easier to plug this on at one time, but I suggest putting parentheses around certain parts, kind of organizing it a little bit, and also think about the parentheses there. The n minus r usually is just a quick subtraction problem that you can do in your head. The numbers aren't going to be too big. A lot of times it's easy to do that in your head, so then you have to, it's one less set of parentheses you'll have to deal with. Okay, so now looking at some examples. 23% of light bulbs in a shipment are broken for each shipment. If a shipment has 50 light bulbs, what is the chance that exactly 21 are broke? Now this is, I know it doesn't sound like a success, a broken light bulb, but that's what we're looking for, so that's what we consider a success. Okay? We have our formula, and the first thing you should do is try and figure out what all of our values are. Our N, our R, our P, and our Q. Our N's our total number of trials. There's 50 total light bulbs in a shipment, so there's going to be our N for that one. We're going to see what's the probability of exactly 21 of them being broke. So 21 is our R, and our P is the probability of success. Again, I know breaking a broken light bulb doesn't sound like a success, but in this situation, it's what we're looking for. So I'm going to put it as 0.23. I'm putting it as decimal now because a lot of times that's, people kind of forget that it has to be in decimal form. Now, complement, if P is 23% or 0.23, Q has to be what you would add to it to get 100%. Okay, they're complements. They have to add up to 100%. So our Q in this case is 77% or 0.77. Now, if I'm going to take the time to put all this in, our NCR, you're going to have to go to get that function, math, then it's PRB, and it should be, I believe it's either the second or third one on your calculator. I don't have that right in front of me. But that's where the NCR should be if you're looking at your calculator. Math, PRB, then NCR. So the way we're going to type this in, first plug in your total, NCR 21. That's going to take into the combination. So that's how to figure out how many ways of these set of 50, how many ways can I rearrange those 21 successes? We have P 0.23 to the R power, which is 21. And our complement, our Q, 0.77. Now, N minus R, this is where I say you need an extra set of parentheses, but I can do 50 minus 21 in my head. 50 minus 21 is 29, so I'm just going to put that up there. Now, what this does is that shows you all the different ways those two values are going to be moved around within that 50. It gives you the probability of those values. So this does the rearranging. This tells you how many successes we're looking for, and this has how many failures we're looking for. Okay? So you can plug that in just the way that looks, and your answer should be 0.136%. Okay, 0.136%. So the important thing here is to make sure you think about what these four values are. Your N, your R, your P, and your Q. write out the formula, and again, I plug it all in at one time. If you have this written out, you should be able to plug it in just the way I have it written there to get your answer. Okay? Okay. Another example of the light bulbs. Things just changed a little bit. 23% of light bulbs in a shipment are broken for each shipment. If a shipment has 200 light bulbs, what is the chance exactly 40 are broke? N is going to be 200. R is 40. Our P is 0.23 again. And our Q is 0.77. So if I'm plugging this in again, the total first, NCR 40. 0.23 to the 40th, that's our R, and 0.77, again, you could write it as 200 minus 40, just make sure you have that extra set of parentheses. 200 minus 40 is 160, so I'm just putting 160 down. Okay. So there's one more example, and this time should be 4.163%. So there are the two examples of the basic ones. I must point out, it says exactly 40 are broke. Okay, that exactly 40 is kind of important. Right. Now, on Dollar Dog Day, there are 84% chance that a person eats hot dogs. If you are with 8 people, what is the chance at least 6 of you will eat a hot dog that day? Okay, so I'm gonna say first figure out my N, R, P, and Q. Now it says you're with 8 people. I'm gonna assume that's our total party. Our total party is going to be 8. Now, at least 6. At least 6 means 6, 7, or 8. So that means our R is not a single value. It could be 6, it could be 7, or it could be 8. So that's not mean we have a little more work to do. Eating a hot dog is 84%. Not eating a hot dog is 16%. Now what this means though is we have to do our combination, our formula, 3 different times. You have to get the probability for each one of these, 6, 7, or 8. Okay, so if I'm setting this up, 8 NCR 6, 0.84 to the 6th power, 0.16 to the 2nd power. Okay, I also have to do it for 7. 8 NCR 7, 0.847, 0.16 to the 1st power, and then NCR 8, 0.84 to the 8th, 0.16 to the 0 power. I'm going to write out all these probabilities, take the time, plug them all in, and you should end up with 25.181, 37.772, 24.788. And now we have to put all these together. We're looking at one situation, but there's multiple outcomes. Think back to 12.1. Or is our key word here. So we are going to add these probabilities together. Okay, since you could get 6, 7, or 8. There's one event we're looking for, but there's multiple outcomes that could happen. So we're going to add them together. 87.741%. Okay, so you have to think about what your R is. Is R exactly one value, like the light bulb examples, or in this case, are there multiple outcomes that could happen? Okay, so I'm going to end this video here so you can take some time, think through some of these, maybe do some practice problems. The next video shows another couple of complicated problems with the formula, but also shows how to use the calculator for these.